The speed of light is one of the most fascinating and mysterious concepts in the universe. It's considered the cosmic speed limit, beyond which nothing can move faster. However, what if I told you that it's possible to reach this incredible speed? While it may seem impossible, the laws of physics make it possible. In this video, we'll explore the fascinating world of the speed of light and how you can get closer to this incredible speed. So fasten your seatbelts and get ready for a journey into the unknown as we explore the limits of what's possible in the universe. First, let's recall what speed is and how light works. So in physics, we call speed a certain value equal to the distance an object travels in a certain time without an exact direction. When an object moves, it increases its mass and the level of its kinetic energy. So the faster it moves, the more mass it will gain and its energy will increase. Therefore, for example, the faster a space rocket moves, the greater the scale of destruction if it collides with a meteorite body, and the more energy will be consumed. In particular, objects can change their speed depending on the medium and its molecular composition due to friction. So this all works for objects that have mass. But what about particles that have no mass, like photons? Let's turn now to what we know about light. Light is an electromagnetic wave resulting from the emission of energy from heated bodies that are perceived by our eyes. However, light is probably also a wave and can be described as a stream of massless particles or quanta photons. Light has a speed of 186,000 miles per hour, and in a cosmic vacuum, it's the likely speed limit for the entire universe. This is what Albert Einstein's fundamental work, which changed the way we understand our universe, tells us: general relativity. If we summarize this theory in one sentence, its main idea is that gravity is a curvature of space, not a force that acts on all objects, and the laws of physics apply equally everywhere. But what does this have to do with light? According to GR, light is constant. That is, it always has the same speed and is probably the fastest phenomenon of all. The reasons for this are the absence of mass of photons and the absence of light moving along the timeline. According to GR and the parabolic model of Hermann Minkowski, Einstein's teacher, time is unified, meaning that there are no separate time and space. Our universe has 4 dimensions: 3 spatial, x, y, and z, and a temporal, t, dimension. Since space is one, everything in it is interconnected. Therefore, depending on your location in space-time, you interact with time and space differently. Let's imagine this using a simple coordinate system with a time and space line. If you're sitting here watching this video, for example, you are moving only in time. Your position in space does not change and you have no speed at all. However, if you decide to go to the store, then you'll be moving in both time and space. It's precisely because of the fabric of space-time we cannot synchronize watches because of the time dilation. This was also proven by scientists in 1971. The researchers placed hydrogen clocks in airplanes on the ground and flew around the world. After landing, it turned out the clocks on the airplanes were running slower by about 1/1,000,000th of a second. Light, on the other hand, moves only in space. It does not feel the influence of time, so if we were to put a clock on it, it would seem to be suspended. Moreover, since light has no mass, it's not affected by gravity. However, if it passes near a black hole or a star, or more precisely along the geodesic lines of space-time near a massive body, its path and energy consumption increase and curve, but its speed remains constant. So if the speed of light is constant and photons are not affected by time, especially in space, how can we achieve or even surpass it? An object with mass, like you and me or a spacecraft, cannot move at the speed of light because it would require infinite energy. However, interestingly, there is another reason. We are already moving at the speed of light. We learned this from Minkowski's model. The faster we move, the slower our clocks go. However, since we have mass, time affects us and we're not physically moving at the speed of light. Our speed is scattered between time and space. Even charged particles cannot reach the speed of light because they also have mass. Scientists are trying to accelerate subatomic particles to the constant of light using linear accelerators with the help of an electromagnetic field, but their speed is always 99.99%. However, at the end of the 20th century, scientists discovered a strange phenomenon, namely the so-called FTL, the movement of particles several times faster than photons. Thus, while observing the galaxy M87 and its jet, a beam of ionized matter ejected from galaxies at high speed. A group of researchers took several pictures of the jet. They noticed that the jet seemed to be moving faster than light. However, this is probably just an optical illusion caused by photons that were emitted later from almost the end of the jet. So it seems to us the light from it travels a shorter distance. Moreover, there's another phenomenon in space that can accelerate particles to the speed of light, but this time it is true: magnetic explosions. When magnetic fields collide with each other, they can often become entangled. If the tension between them increases greatly, they will break apart, which will throw all the charged particles away in an ultra-high speed. This process can be considered a natural particle accelerator. However, this is all about measurements in a vacuum. Recall that light travels through a certain medium, such as water, more slowly than in a vacuum. So charged particles can move faster than light, but in some kind of medium. The proof of such FTL motion is Cherenkov's irradiation. When a particle moves faster than light in some medium, it polarizes other particles, or in other words, it repels or attracts. When the charged particle moves further, the electrons are returned, which causes the Butte glow of the irradiation. One hypothetical subatomic particle could be another competitor to light in speed. In 1962, scientists considered the possibility of the existence of particles that would be faster than light with the inclusion of GR. But in their work, they noted that such particles could move faster than light from the moment of their appearance and not by increasing their speed, which is not contrary to GR. These theoretical particles were called tachyons. Unlike other particles, a tachyon has energy, but its mass at rest is imaginary, meaning it has a mass only when moving faster than light. It's also likely that an approaching tachyon will be invisible because light travels slower than it. In particular, it's also hypothesized to speed up when it loses energy. It's believed that a tachyon is formed when energetically strong cosmic rays hit the Earth's atmosphere. So far, the existence of tachyons has not been confirmed, and therefore light can be considered the speed limit at the moment. In addition, tachyons can lead to logical temporal paradoxes. For multiple observers, a tachyon can travel to the future and the past. So, if a tachyon can travel back in time, this leads to the classic causal paradox, for example, in which a traveler can affect his own existence and prevent his own birth or send a message to himself in the past. However, does superfast motion really lead to traveling back in time? In fact, faster-than-light travel is not necessarily the cause of paradoxes. For one observer, a spacecraft whose speed exceeds the light constant will travel back in time, so it will also land in the past before it took off. However, according to the physicist Sabine Hossenfelder, such paradoxes are possible from the standpoint of special relativity, not GR. Thus, another observer, for example, can move along with matter in the same direction, forward in time, which means that the ship for him moves only forward, and therefore cannot break the causal relationship and first land and then only take off. In fact, the second observer follows the entire process, and therefore does not see any logical violations that arrive from the perspective of the first observer. who believes that the ship is moving backward. So we can't simply accelerate to the speed of light. However, we know that light travels in space-time. What if we could bend space so that light travels a longer way than the object around which space is deformed? It sounds fantastic, but scientists are considering this space travel option. This concept is called the Alcubierre drive or warp drive. The idea of a warp drive is to stretch the canvas of space into a wave which should hypothetically compress the space in front of an object, such as a ship, and expand the space behind it. Thus, the ship will essentially move on this wave in a so-called warp bubble faster than light. Alcubierre's drive consists of three parts: the inner bubble or passenger space, where time passes more slowly than in the general space, and two outer parts, a shell of negative and positive energy and normal space without changes. However, warp drive requires a conceptual negative energy, which is impossible according to GR, but can exist in quantum theory in small quantities. This is one of the main problems of this theory. So to be able to implement it, it is desirable to find a method using positive energy. In 2021, astrophysicist Eric Lentz was able to develop such a concept. According to his model, such a bubble should contain a liquid plasma with a huge mass, about 10% of solar energy, and electromagnetic fields that would be located around the ship in the shape of diamonds. Such a bubble would be able to transport the ship, but only at a speed close to the constant of light, meaning that such a drive would not be able to accelerate to FTL. So far, it's impossible to confirm whether warp drive can exist without negative energy, as well as to start experimental work on it in general. However, if warp drive can work without the use of negative energy, then in the future, we'll be able to travel to distant planets much faster than with current technology. Another way that negative energy could hypothetically allow us to travel in time actually faster than light is through Einstein-Rosen bridges or wormholes. Einstein first came up with the idea of the existence of such tunnels from one place in space to another. It's believed that wormholes can be connected at gigantic distances of several million light years. However, although they have not yet been found, wormholes are very unstable, so they can quickly disappear due to negative energy. In addition, they're probably not as wide as we imagine. Also, because of this energy, wormholes must be small for a person to pass through. Therefore, until scientists find a way to keep both wormholes stable and large enough to confirm their existence, we cannot use this method for travel. Finally, quantum physics offers an interesting hypothetical way to transmit information at speeds greater than the light constant. This method of FTL communication is called quantum entanglement. In fact, quantum entanglement is an inseparable combination of two quanta that can exchange information with each other faster than light, despite the distance. Particles communicate by changing their state, for example, by changing their spin or energy. So during a long-distance travel in space, hypothetically, an astronaut could send a signal about possible life on the exoplanet under study, and this signal would reach the controller almost instantly. However, in reality, it is their variability and randomness that's the main problem that makes this concept of FTL information exchange unlikely. Quanta cannot be brought into a certain state to transmit any data because then the particles will break the connection with each other, and the particle whose state has not changed would show random results. So communication in this way would be impossible and probably not even reach the speed of light, because information cannot be transmitted at a speed greater than the light constant according to quantum mechanics. Moving at the speed of light or even faster gives us a serious advantage in space exploration. At the moment, we're not able to achieve this speed, but the hypothetical ideas of warp drive and tachyons, as well as the use of knowledge about FTL in different environments, can be an important step towards further research into ways to achieve the light constant. However, this is still in the distant future. So our priority now is to develop the technical knowledge we have so that our main goal in the study of space-time will be speed.